Hi, I'm Mark Weitzman, and welcome back to Path Integrals in Quantum Mechanics, and we'll try and finish everything up this video and get the most important formula. So one of the things you do in quantum mechanics and quantum field theory is often you add what are called like forcing terms to the Hamiltonian. So what we're going to do is we're going to deal with this Hamiltonian, and we're not really saying this is the real Hamiltonian, but we're using it sort of as a mathematical crutch. We're going to take like what are called functional derivatives with respect to f and with respect to h. Those are going to bring down factors of q. Then on the end we're going to set f equals 0 and h equals 0, which gets rid of this term, and so we're back to our path integral with just h. It's just a trick to get some formulas. So let's write down our propagator. So, and we usually put a f comma h here. So when we set fh equal to 0, we just get our normal propagation amplitude with our Hamiltonian, original Hamiltonian. Now what we can do is we can take functional derivatives, and functional derivatives are just like plain old derivatives. There's nothing really fancy in them. In case you want a real good book, this book treats quantum field theory from both the functional point of view, path integral point of view, Schrodinger operator, and the Heisenberg approach. So it does all three approaches very well, and they really discuss in a more mathematical way functional derivatives, functional integrals, functional differential equations, all kinds of things. It's a very good book. It's a book that sort of reviews quantum field theory. And if you already know some quantum field theory, this is a good book that will review it all for you, because it only covers the basic things. It doesn't cover like real fine details. It does some calculations, but not as much as in beginning quantum field theory books. Okay, so I want to take a functional derivative. What we do is we go have 1 over I, and we usually indicate functional derivatives by del instead of d's, del f of t1. So if we apply that, so what's going to happen here? We're going to get, we're taking the derivative with respect to f of t1. So we have this exponential, it's going to stay here. We're going to get an I, that's why I have a 1 over I here, that's going to cancel that. Then I'm going to take this whole thing, I left out the dt here. So I'm going to have something like f of t, q of t, which is going to come down outside the exponential. We're going to take del f of t1. Okay, so when we do that, actually I have an integral dt. So this is equal to, I can bring it inside the integral of dt, del f of t1, f of t, the q of t is. So now here, this is a well-known formula. This is just going to be del t, the delta function, t minus t1. It's the same thing as if you were taking like the partial with respect to xi of xj. It's equal to del ij. This thing is exactly the same. The variable we're differentiating is defined at the point t1, and then 0 if t is different than t1, and it's infinity basically. So that's why we get the Dirac delta function. And then this whole thing is equal to q of t1. So when we evaluate this, we end up getting the integral of dp dq q of t1, and then that whole e to the I dot dot dot, exactly that. And if we set this at f and h equal to 0, we're going to get our usual, well, I erased it now, but we're going to get the thing with an operator insertion over there, q of t1. So the main formula that we want to take away from this whole thing, I'll write it out completely. The time ordering symbol applies to every operator to the right of it. So in a sense, we're just using that formula over and over again. We take the derivatives that will bring down a q of t1 all the way up to an h of tn, just a time ordering product. And to get this, we have to, after we're done with that, we still have this exponential. These forcing terms are still there. We have to set f equal to h equal to 0. So that's probably one of the most important formulas of this chapter, and I'm going to write down the next one. Our aim here is to do perturbation theory. So we set like h equal to h0 plus h1. And the idea is that h0 is a Hamiltonian we know how to deal with. We know its eigenvectors and we know its eigenvalues. And h1 is usually a small perturbation. And so then what we do is we compute, I'll explain in a second why I'm using the vacuum here instead of coordinates. We compute the vacuum to vacuum transition amplitude. And this is equal to the integral dp, path integral So this is sort of what we had before. Now the idea is we can take this, we can write this in a funny way. We can write this as e to the minus I, the integral from minus infinity. So what we're doing is we're sort of factoring out the H1 part, the part that we don't know how to handle. We're factoring out that here. And we're replacing, notice what happens. Whenever we have a 1 over I, when we apply these functional derivatives to what remains, this part will always bring down a P, and this part will always bring down a Q. So imagine H is, this is going to be like squared, and this is going to be like cubed or whatever. It's going to bring down a P squared and a Q cubed. So it ends up being H of P comma Q. But we take the functional derivatives of, after we move that, we get so this whole part down here, because it's based on H0, we assume that we know how to handle it, because we know how to handle H0. This is the part that we don't know how to handle. But now we're turning it into derivatives. We can expand this exponential in powers of H1. We could take like the first term, 1 minus I H1, just apply these functional derivatives to here, and we get something that we can evaluate. So that's how, we'll see more of this in the next few sections of the book, but that's how perturbation theory works. Now I skipped over with the vacuum to vacuum transition amplitude, and it's treated in the book. It's basically the idea that these are the boundary conditions, and if we go from minus infinity to infinity, and we have like this is the ground state, it ends up only the ground state will be in the wave function at minus infinity and plus infinity. And you can look in the book for the argument. It's based on a E going to, H minus I epsilon argument. This will like end up being an exponential with a minus I and be exponentially suppressed. And that's one way to think about it. Be a 1 here. No, I think I had it right. Another way you could think of it is in Peskin and Schroeder, they do this in another context, but it's sort of like you have this is the integration path, and you sort of rotate it and by a certain angle, theta, and that introduces the imaginary part, which will end up killing it. So the details are in the book, but the main thing is to remember this formula and this perturbation formula, so we'll use that a lot. Thank you very much. See you next time.